Hello. Sorry for the delay, but now I'm ready. Is it a bit loud? Okay. So the very final lecture on linear algebra today, and I'm going to talk about orthonormal systems. Orthonormal systems. And if you managed to do the last problem on Wednesday, you have started on this, but I'm going to talk about the orthogonal complement. And I start in the plane. And then I do it in space. And I can do special things in the plane and special things in space. But I'll also give you a general method. And then I'm going to give you some illustrations of this factorization of a matrix. And it's a symmetric matrix, so you can factorize it in an orthogonal matrix transposed times a diagonal matrix, and then, no, it's Q, and then Q transpose, like this. Let me just plunge into it. An orthogonal complement, what is that? So suppose that you in Rn is given a subspace U, and then by the orthogonal supplement or complement to U, we understand what do we understand? We understand this set of vectors and these are, of course, vectors in our domain, our vector space Rn. And all these vectors that are, I better write it in this way, are orthogonal to the given, or to all the vectors. And this is all vectors U in the subspace U. That is, you take any vector here, and then you see to it that it is orthogonal to V, and then you get the orthogonal complement. So let's start by looking at the thing in the plane. So the plane, this is R2. And we are given a vector and this is arbitrary. but we're given a vector. And then we consider the subset of R squared as the span of this vector. So this is the span of the vector V. Now, how does that look? Let's try to figure that out. So I make a drawing of my vector V, and I draw it from the origin, so to speak. But what is then the span of V? The span of V is all vectors parallel to V, and this means all vectors that in a sense lie on this line. You can take this vector, for instance, or this vector. So the whole line here is the subspace U. Now, the orthogonal complement to this, that will be all vectors that are perpendicular to this line. So let me draw this. So this is a line that is perpendicular to this line. That is, this angle here is pi half, or 90 degrees. And in order to describe this, or the space here, you need a vector on this line here. So you could take, say, the vector perpendicular. Normally we denote this as the vector with a hat above it. So this vector here will describe all of this line, and if you write it down here, you get U and then the sign here, and this is just a sign saying that these are the vectors that are perpendicular to U. And this will be the span of this perpendicular vector we had. Now, something I'm going to use later on. What is the dimension of this U subspace here? Yeah? It's 1. What is the dimension of this one? This is also 1 for the same reason, yeah? So you have that the dimension of U is 1. You have the dimension of the orthogonal complement is 1. And they sum up to 2. But be careful, because even though the sum of these two subsets had the sum of the dimensions of it is 2, it's not all plane vectors that are in these subsets. You see, in U you have vectors in that direction, and in the complement you have vectors in that direction. But for instance, you don't have this vector here. It doesn't belong to any of them. So bear that in mind this afternoon. Okay. Now, let's continue to the space. So we are in space R3, and we consider a particular vector. And this is the vector with the coordinates, or the elements 1, 2, minus 3. And we want to find the orthogonal complement when U is equal to the span of this vector V here. Again, I can try to draw this. Let's say I draw this. I take the origin and then I draw the vector V here. Then obviously the orthogonal complement will be all vectors lying in a plane that is perpendicular to V. So let me try to see if I can illustrate that. So you have this plane here, and you should imagine that this vector here is orthogonal to this plane. So this line here is 90 degrees, and you have another angle here which is 90 degrees. So it's perpendicular to that plane, and this will be my orthogonal complement. So you can say here that the orthogonal complement is a plane with a given normal vector. And now I'm going to use something that you learned in high school, or something I believe you learned in high school. And that is, if you have a, well, I'll just write down, is a plane with the normal vector. It's a normal vector V. Oh, I'm still in the wrong mode here. Yep. And you know, you were in high school, you were taught the equation of a plane with a given normal vector. So if you have this, probably you will recall this, where this is a plane through the point x0, y0, z0, and with the normal vector that is a, b, c. So, and you can see it because this is actually, if you take x, y, and z as a running point in the plane, then this is just a scalar product of the normal vector a, b, c, times a vector in the plane if x, y, z is in the plane. So this is the equation for the plane. And this becomes particularly simple in our case because we have placed the plane at the origin. And this means that all these numbers here are 0, and we have this normal vector, so you end up with 1 times x plus 2 times y, and then minus 3 times z is equal to 0. This is the equation. But you want to have some vectors. You want to have a basis for this, this plane here. And the way to do that is simply to solve this equation with respect to x. And you get yeah, I try to do it. I have another number here, but let's see if this will be okay. I move this to the other side. I have minus 2y plus 3z. And then if I call this number here for s is a free parameter, and this number here for t, I can write down the solution. You have x, y, z, and we know that this will be the structure of the solution. And we have put y equal to s, so there will be a 1 here, and we have put z equal to t, 1 here and a 0 for y. And what about x? We get minus 2 s and plus 3t, like that. So here we have two linearly independent vectors, and they span the subspace. So let me write this. We have that this is the span of the two vectors, minus 2, 1, 0, and then 3, 0, 1. Now again, we have that the subspace U as before. This is this right line through that coincides with V here. It's in the direction of V. So this is our space U, and this is our orthogonal complement. So I can again look at the dimensions. So the dimension of U is 1. It's a line. The dimension of the orthogonal complement, yes, you have two. You have two vectors in the basis for the orthogonal complement, so the dimension is 2. And this time it sums up to 3. So you will think there is a relation to this 3 here, and there is. We'll see that shortly in the more general case. Now, what if we start with a subspace that is spanned by two vectors? Now we have two vectors, u1 and u2 in R3, sorry. We are looking at R3. So we have a subspace that is the span of these two vectors. u1 and u2. How do we, in this case, construct the orthogonal complement? Let me try to illustrate this. I have a vector u1 here, and then I have another vector u2. So these two vectors span a plane. I can illustrate that by drawing this parallelogram here. So it is this parallelogram plus all that is outside this parallelogram in this or in these directions. Again, we're considering the origin. And the orthogonal complement will then be a line that is perpendicular to this plane. So it will be perpendicular to that vector, or like this, I should draw it. And then it will be perpendicular to that vector. Now, this is easy. You know a vector that is perpendicular to both these vectors here, u1 and u2, you are in 3 space. Yeah. The cross product. That's true. So you have simply that if you take the cross product, you will get a vector in that direction. I write here u1 cross u2. So in this case, you simply have that the orthogonal complement is the span of u1 cross u2. This was the easy part. What happens if the dimension is larger than 3? This is what I'm going to tell you now. And this will be the start of the general method. So a general method of finding the orthogonal complement. So we are given in R4 is given a subspace U, and they're spanned by these 3 vectors here, U1, which is all ones, 4 ones here, and then the next one is you have 3, 1, 1, 3, and then finally you get 2, 0, 0, 2. So your subspace U is spanned by these 3 vectors, and we are asked to construct the orthogonal complement. So how do we go about doing that? Yeah, we know one thing is that if we have a vector x in the orthogonal complement, then we know that we should find x, and I can write here such that u1 times x1 is equal to 0, and u2 times x1 is equal to 0, and finally u3 times x is equal to 0. So this should be fulfilled for a vector in the orthogonal complement. Now I claim that if this is the case, if x is orthogonal to these 3 vectors, it will be orthogonal to all of u, to the whole subspace U. Yeah?
Yeah, I think it's not linearly independent, the basis.
I know. But that will be apparent shortly. That will be part of the solution. Okay, thank you. So my claim is that if this is the case, then X will be orthogonal to all of U. And this is easily proved. So I'll just write down the proof here. And now I take a general vector in U. Since U is the span of the three vectors, U1, U2, and U3, then a general vector could look like this. A times U1 plus B times U2 plus C times U3. And if you multiply this by your vector X, then you can use the rule of computations, the distributive rule, so you can multiply this on each term here. You get A and then U1 times X plus B U2 times X, and then plus C U3 times X. But X is constructed so that all of these, or the dot product with U1, U2, and U3 are all 0. So this is 0, this is 0, this is 0. So the product of X and a general vector in U is 0, so X will be orthogonal to all of U. So if we can find all the X vectors, then we have found the orthogonal complement. So let's do that. Now I'm going to write down a system of equations, and I will show you that the system of equations is equal to the three equations I have up there, U1 times X and so forth. So I write down a matrix which is my three vectors as rows, 1, 1, and then 3, 1, 1, 3, and then 2, 0, 0, 2. And then I multiply this by x1, and this is my x vector. I have the coordinates x1, x2, x3, and x4. And this should be equal to 0. And you can see if you multiply this into this matrix here, you get for the first row here, which is U1, you get U1 dot x, and this should be 0. U2 dot x is the second row, and U3 dot x is the third row. Now, this is a system of homogeneous equations, 3 of them, and what is the solution to such a system? Well, you can consider it a matrix mapping. So you're mapping X into 0, and then you know immediately what that is. Yeah, it's a kernel. It's a kernel of that mapping, and so I can write it in this way here. So it's a kernel of the three vectors u1, u2, and u3, but you have to transpose them. So you see, in order to write down this system of equation, you transposed the vectors. So we simply have to find this. And now you are... I'll just take what this means, because this is... or let me just try to solve this. So when you have this system of equations here and you want to solve it, you take the augmented matrix. And this is 1, 3, 2, 1, 1, 1, 3, 1, 1, 3, and 2, 0, 0, 2. And you could, if you take R2 minus 3R1, you get a 0 here, and R3 minus 2R2, you get a 0 in the third row, you get 1, 1, 1, 1, and then you get 0. I better take the right-hand side, because I called it an augmented matrix. So you have 0 here. But if you take minus 3 times this one and add it to this line here, you get minus 2, and 0, 0. And if you multiply this by minus 2 and add it to that, you get 0, minus 2, 0, 0. And now you can see these two are similar, so you can just subtract this from this and you get all zeros, and you can multiply this row here by minus 1/2, and I can then write down the fully reduced matrix. So I get 0, 1, 1, 0, 0, and all zeros down here. But I want to get a 0 here as well, so I subtract this from the upper matrix. So I get 0, 0, 1, 0. So what I can read from this is, if I interpret it as equations, then x1 is minus x4 and x2 is minus x3. And I can write down the full solution: x1, x2, x3, x4. If I call this for, let me call this for S and this for T, then I have this times S plus this times T, and I have this is not good. Let me do it as we used to do. x3 is S and x4 is T. Then you get a 1 here, and you get a 0 here. You get 0 or 1 0 here, and then x4 is minus, or x1 is minus x4. That is minus 1 here, and then x3 is or x2 is minus x3, so you get a 0 here, and you get a minus 1 here. Something's wrong. Yeah. No. In S, it's... Yeah. Because this was x2 that was equal to minus x3. And here you get minus 1, 0. Okay. Sorry about that. So what you can see here is that the orthogonal complement is the span of these two vectors here. 0, minus 1, 1, 0. And then minus 1, 0, 0, 1. But what about you? You were spanned by 3 vectors. Yeah?
But 2 of them, they are not linearly independent.
No.
They are parallel.
Yeah.
So they only have the dimension of 2.
Yeah. So it's U is really 2-dimensional. So you only need 2 vectors in order to span U. You see here that if you add number 1 and 3, you get the second one. So you can do without one of them. So I could choose the 2 first vectors, and that is I write here that U is the span of 1, 1, 1, 1, and the other vector here, which is 3, 1, 1, 3. Now, you can see here that they are indeed orthogonal to these vectors. If you multiply these 2 vectors, you get minus 1 plus 1, that is 0, and this one, minus 1 plus 1, 0. Similarly here, minus 1 plus 1, 0, and so forth. So these 2 vectors are orthogonal to the vectors spanning the orthogonal complement. But they are not orthogonal to each other. Luckily, these 2 vectors, and this is a coincidence, they are orthogonal to each other. You see, if you take the product of these 2, you get 0. But let's try to revert to the question of dimension, because now the dimension of R4 is, and this is a structural theorem I'm just writing down, it's the kernel of the mapping, and then it's plus the dimension of the image space, or the range of the mapping, like this. We just saw that this here is, or the orthogonal complement. This is the kernel of this. So this will be then the dimension of the orthogonal complement. This one here, does anybody recall what that is? It's the rank of our mapping matrix. Yeah. So, and this is equal to the dimension of U. So, here we have it. This is the dimension of U. So, I could write it down more generally, because if you have an n-dimensional space here, then you still have this sentence. The dimension of the orthogonal complement plus the dimension of the subspace is equal to the dimension of the domain. Okay. I think I just have to continue in order to finish on time. So, but I'll just take out these. No, it's here. Now I'm going to illustrate this one. But remember, when you have, say, an orthogonal matrix, what I'm going to do now is that I'm going to have every positive orthogonal matrix Q, and now I'm talking about, this is my example, constitutes a rotation of the standard base. And let me try to illustrate this. So what I'm going to do now is that I'm going to draw the unit circle that looks somewhat like this. And then I will take a new basis, and I use this as the first basis vector. And if it should, since it's the unit circle here, it is normed to be a unit vector. And then I can take the orthogonal vector here, and then I will call this for Q2. And then my matrix here is Q1, Q2, these two vectors. And if I introduce the angle here, I call it U, this is the angle U, then you know what the coordinates of this vector is? Yeah. The coordinates are cosine u, sine u. This is simply the first coordinate, cosine and sine. And now for Q2, remember you could take the perpendicular vector, and that would be minus sine u cosine u. What I'm going to do now is that I think of Q as a mapping matrix. And if I do that, then I can ask, what is the image of some vector x? So let me take a vector. Let this be my vector x here. And you're going to do an exercise, I don't recall which, where you're going to look into this problem. But the thing is that when you use this mapping on this vector here, it is rotated by the angle u, say into, the length of the vector doesn't change. So it'll be on this circle here, but it is rotated u in the, so this angle here will be u, and this is the resultant vector y. So I write here that this appears by rotating x and then with the angle u. Now if you do the same thing with the transpose of T, and remember for an orthogonal matrix, the transpose of the matrix is equal to the inverse of the matrix, then this appears by rotating x with minus u. Now, I revert to an example we saw on Wednesday. We had this matrix here, 3, 1, 1, 3. And then we computed the eigenspaces. First we computed the eigenvalues, which is 4 and 2, and then the eigenspaces, 1, 1. And for the eigenvalue 2, we have the eigenspace minus 1, 1. Then you can write down your Q, because you use these, or you normalize these vectors here by the length of the vector, which is square root of 2. So you get 1 divided by square root of 2 and 1 divided by square root of 2. This is the first vector here. And then minus 1 divided by square root 2 and 1 divided by square root of 2. And if you're looking at this mapping here, or this factorization, then you get that this diagonal matrix will be 4, 0, 0, 2, with the eigenvalues in the diagonal, and in the same order as you use for this, for the eigenvectors in Q. Now, if I look at this factorization of the matrix, then I can interpret that in terms of geometrics. Let's try to do that, because consider A to be a mapping matrix, then you have Q, and then you have your diagonal matrix, and then you have Q transpose times X. And you want to find out what is Y. So in this case, it's really simple. You have this matrix. You can just plug it in. Now we're going to interpret that geometrically, because Q here, we have just seen that this is a rotation of this. And multiplying with this diagonal matrix means a stretching of the vector you get from here, stretching in the two directions of the eigenvectors. And then this is also a rotation with the opposite sign as QT. So let's see how that looks. So I draw here, and I draw the unit circle. Like this. And I take, again, a vector x here. Now, the angle that Q will rotate any vector or figure, that is pi fourth, corresponds to this. You see, if you draw this unit vector here, you'll get pi fourth, like this. So the first thing you should do is that you should rotate your x in the clockwise direction by pi fourth, and it will look something, say, like this. And this is actually the direction of your rotated coordinate system. So what you do now is that you stretch the coordinates for this vector by 4 in Q1's direction and by 2 in Q2's direction. So let's try to do that. Let's call this x1. And then if you project this, you get the first coordinate here, and then you multiply it by 4. It will be 2, 3, 4. So this will be, say, in the Q or the Q1, Q2 system, this will be the first coordinate there. And if you project this down to the Q2 axis, then you have 1, 2, it will be doubled. So if you draw this rectangle here, you will get this vector here. So this is the next stage. Now you have this vector, but you're not through yet because you have to rotate it by pi fourth. So you do that, and you end up here. And I draw it. So this is the result, A times x of the vector. Now you can check how good my drawing is, because you can just compute 3113, and this is basically this vector here would be, say, 1, 2. This vector here. So you multiply it by 1, 2, and then you get 3 plus 2, that is 5, and you get 1 plus 6, that is 7. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5, 6, 7. They may not be equidistant, but pretty good. Anyways. So have fun with the exercises, and remember there's a test at 3:30. Okay, thank you.